Okay, good morning, everybody, and thank you all for coming, and thank you, Tim, for that introduction. So I've, here we go, turn it on. Good. So I hope you've enjoyed these live polls as you've been getting comfortable in your seats this morning about your reactions to last summer's eclipse and the topic of today's talk. The word cloud is interesting. The eclipse was indeed awesome. Some of you might have found it anticlimactic. I'm sorry if it was cloudy. Our president must be in the audience. And he's live tweeting the talk. And many of you, it would appear, traveled to see this eclipse like many, many other Americans did. And it looks like those of you who did not stay home in Michigan drove to points south along the path of totality. Some of you were out west or in the middle part of the country, and some of you were really lost. I don't know what, what you people were doing out here. But so I think the point of this is that this eclipse was a major event for not only our regulars at Saturday Morning Physics, but for our country. And what I'd like to tell you about is give you some sense of how that was, the scale of the event. It was the first total eclipse visible from North America in 38 years, and so many people had never experienced one. But also it brought the country together in ways that very, very few things do. So that's the topic of today's talk, the Great American Eclipse of 2017, experienced by many. This eclipse went coast to coast from the Pacific Northwest to the southeast and right across the middle of the country, past a number of populated areas. The point of greatest eclipse here, this dark circle, was somewhere near Paducah, Kentucky. So many, many people live within a few hours' drive of this eclipse. I will show many such maps and many eclipse predictions and so on in this talk. And almost everything I am showing comes from the 5 millennium canon of solar eclipses from minus 1999 to 3000. That is a publication of NASA. Fred Espenak and Gene Meas put it out in 2006. And then that's available on NASA's website. And then there's a wonderful searchable web interface to this that lets you generate Google Maps and interactive materials, GPS files, Google Earth files, and so on the website there below. So I'm very indebted to these resources for helping put this talk together. So this may well have been the most watched, the most anticipated eclipse, if not an celestial event period in history. The University of Michigan School of Institute for Social Research and Professor John Miller there did a survey with support from NASA. They surveyed a group of Americans, a statistically uniform sample of Americans in the spring before the eclipse, and then they followed up to see what Americans' eclipse viewing habits were and what they planned to do and how they experienced it, what they knew about science. So according to this University of Michigan study, 154 million adult Americans saw this eclipse directly. If not the total version of it, then they experienced the partial phases of the eclipse like you did if you stayed home in Ann Arbor. 61 million more Americans viewed this eclipse online. Altogether, 88% of the population of this country experienced this eclipse in some way, either in person or online. 20 million people traveled somewhere to see it, and many of you are among that group. And part of why it was such an event is that it was the first coast-to-coast eclipse in a century. So there had never been in anybody's lifetime really an opportunity across the country for this many people to experience something like this. Moreover, it happened at a great time of year, late August. Many people have time off, they're on vacation, the weather is nice, it's good to be outside, you can combine this with the vacation. So, and finally, there was great weather across the whole country for most of the path of that eclipse. I see a few of you said it was cloudy. I think that tended to be spots further east, but most of the country saw really great summer weather and clear skies on the day of the eclipse, which made for great viewing. So how big was the eclipse? So you can go to Google Trends, and you can see what people were searching for when. So here's eclipse. Of course, search has peaked in the days and weeks before the eclipse. Not nearly as big as the Super Bowl, about as big as hurricanes, and there may be more total searches for Christmas, but it never actually peaked at a level above the eclipse. So the level of interest in this event was on par with the very biggest events that happen at any time in the year. Things I didn't put on here include Bitcoin, which was a big bump in December when the price went through the roof, and so on. You could also break this down a little more by region. I was interested to see where people were searching for the word eclipse. And interestingly enough, it pretty much tells you where it went. Half of those searches may be mine. There are also other digital fingerprints that we left behind. Google Traffic showed signs of a mass migration in progress in the hours after the eclipse. You can see traffic heading away from the center line. Here north of Memphis, it is red heading north and it's yellow heading south. So apparently the totality went right through there. So you can trace the fingerprints of this eclipse in our data. And finally, this really amused me a lot.
Once upon a time there was light in my life, but now there's only love in the dark. Nothing I can say, a total eclipse of the heart.
We are so predictable. Admit it, you did that too. Okay. So, and you're welcome for getting that song stuck in your head again. I've had it stuck, now it's your turn. So like I said, this was the first total eclipse visible from North America since 1979. So this is me in 1977 in my backyard in Hudson, Ohio, with the 6-inch telescope that I had built in my basement. You can tell it's the 70s because of the hair and the bell-bottom jeans. And I'm saving those jeans. I'm hoping they're going to come back in style one of these days. But as a kid, I was very interested in astronomy. I had nice dark skies in the neighborhood where I grew up and spent a lot of time as a kid outdoors at night learning my way around the sky and looking at solar system objects and nebulae and so on with my telescope. And these were three of my best friends, Jeff, Rob, and Steve. And sometime between when this picture was taken in 1977 and a year and a half or so later, I read somewhere, probably in my subscription to Sky and Telescope, that there was going to be a total eclipse in February 1979, and that it was going to be the last eclipse visible from North America until 2017. Now, when you're 14 years old, you do the math, 2017, I'm going to be 53. That's the future. That's infinitely far away. I'm going to be so old. I might have kids. You know, that's how old I'm going to be. That's incredible. But I really wanted to see this eclipse. So we started planning a road trip. Now, none of us could drive. That was a bit of a problem. So we were able to convince Steve's dad and most importantly, our 8th grade science teacher to rent an RV and get this trip together and drive to the site of the location of this eclipse. There's one other person I will mention for the Saturday Morning Physics audience who might have been part of this story, but moved out of town about a year beforehand, and so was no longer in this circle. But the future Professor Tim McKay was a classmate of ours, and but he moved after 8th grade. So those of you who know Tim will be amused by that. This was the path of the last North American solar eclipse in February 1979. It passed through the Pacific Northwest, much like the most recent one did, but then it turned north instead of diving south and headed up into Canada. So we drove from our hometown of Hudson, Ohio, in February, 1,300 miles over a couple of days, and stopped overnight in Winnipeg. And this was before, you know, you had the weather map on your phone and stuff like that. But we somehow found out the day before that Winnipeg was going to be cloudy, which was where near where we had intended to visit it. And so the next morning we set out in this RV, kind of just hunting for a gap in the clouds, and found one near Melita, Manitoba, where we pulled off the side of this godforsaken highway, and you know, saw the eclipse. So 2017 seemed like the future then, but now 1979 seems like history, seems like the past. Here are some things that were going on in 1979 for those of you who did not live through that time yourself, or want to trip down kind of some mostly crummy memories of 1979. It wasn't a great year. 3 Mile Island happened in 1979. Terry Bradshaw was the MVP of the Super Bowl later that year. You know, before he was a television announcer, did you all know he was a football player? The Iranian hostage crisis developed later that year, causing Time to name Ayatollah Khomeini the man of the year. There were lines at gas stations and fuel shortages. You know, gas at $1.10 a gallon sounds cheap, but in 1979 that was pretty expensive. The Nobel Prize in Physics that year was given to Weinberg, Salam, and Glashow for what we now call the Standard Model. Particle physics still going strong. What else? McDonald's introduced the first Happy Meal in 1979. You could buy a Ford Pinto, pretty awesome set of wheels. Mork and Mindy was one of the most popular shows. And finally, computers were just starting to make their way into Americans' homes. Anyone remember the Trash 80? This was that, and many of us learned to program on something like that. Okay, look at this. It's upgraded $3,400 for a computer in 1979. That's probably a $15,000 or so in today's dollars now for this thing. Technology has really, really overtaken us when it comes to computers. And then the #1 hit the week of the eclipse.
Exactly what they're thinking. And you think I'm so come on, sugar, let me know. If you need me, just reach.
So let's move right on. So the other thing about the winter of 1978-79 is that it was the coldest winter in North America since 1895. It was a bitter, cold winter, and so here we were in the plains of Canada. It was really cold, but here we all are, moments before the total eclipse. I'll just let this roll for about 30 seconds, and you can see. That's me in the orange jacket. we were. Just out of curiosity, is there anyone in our audience today who saw that eclipse? A few of you. Did you go see the in Winnipeg? Yeah, beautiful. So we were probably somewhere close by.
Right before it was pouring rain, and we decided to fly anyway.
Uh-huh.
I woke up in the morning and opened the curtain, and I yelled out, "It's clear!
It turned out to be a beautiful day, but it was a little scary there for a moment. Okay, so, however, this eclipse was not nearly as widely seen because of the northern trajectory of it. It wasn't over as many populated areas, and of course, the time of year made it less attractive, except if you were crazy to go watch it. But it was covered widely on television. Here's just a short sampling.
This is indeed a special events broadcast of a genuine special event.
A total eclipse of the sun, visible today over North America.
Frank, this is absolutely amazing. There you can see it. Isn't that amazing?
It was the last total eclipse of the sun for North America until the year 2017.
The solar eclipse in ABC.
Okay, so Walter Cronkite knew it wasn't going to be another eclipse until 2017, and we knew, but I'm interested in when we knew and how we know. It is one of the things that is fascinating to me about these eclipses is that while many things in science are surrounded with various degrees of uncertainty, or particularly about predictions going way into the future, everybody knew last August exactly where to go and exactly to the second when it was going to happen and how. So how do we know? These are the eclipses in the world over the 20-year period from 2001 to 2020. And you see they are not rare, but at the same time, the chances that any one spot on Earth experiences a total eclipse, those are the purple bands, or orange, or whatever color that is, are a little more rare, and furthermore, this pattern looks kind of random. So, how do we go about predicting eclipses? So, one of the things I never saw in the coverage of this eclipse was actually when the first accurate prediction of this particular eclipse was made, and so I have gone digging, and the earliest reference I can find to this, I mean, people have been. Even ancient people knew something about predicting eclipses, but often it was just, there will be an eclipse somewhere on this date. The ability to accurately predict the trajectory and the time is a relatively recent thing, I believe. And the earliest prediction I've been able to find that gets this eclipse just right is from a work by Theodor von Upsala in 1887 in his Canon of Eclipses. This is an amazing work. It catalogs the elements and the central lines of 8,000 solar eclipses and over 5,000 lunar eclipses over a 3,000-year period. He's doing all this by hand. This is and so you can see I've turned this right side up. Here's his path for August 21st, 2017. The circle on this line there indicates the point of maximum eclipse, and he's got it correctly located somewhere near Carbondale, Illinois. Okay. So at least 100 and whatever that is, 30 years ago, someone saw this coming. Now, people at the end of the 19th century were living in an age of maybe the high watermark of 19th century computational astronomy, where this work is really done in a painstaking way by hand. And here's another work from around the same time by Chauvenet. Both Chauvenet and von Upsala were perfecting techniques and applying them that had been invented in the mid-1800s by Bessel. We still talk about the Besselian elements of an eclipse. So here's an illustration from Chauvenet's work from 1891, his Manual of Spherical and Practical Astronomy. He devotes about 100 or 150 pages to eclipses in this book, and the rest of it is about how to use a sextant and a transit telescope. It's very much focused on nautical applications of eclipses. But he kind of says, our calculations are way better than these pictures. And really, if all you want to do is make pretty pictures, there's lots of shortcuts, and you'll figure it out. He says these will be readily apparent to the skillful computer, and he's talking about a person is a computer. Before computers were computers, they were people who did computations. And he even goes into some detail about how you should do these computations, you will want 6 pieces of the best stout linen paper. 21 by 16, you want to line them like so your figures line up. And plan on both sides of this for a total eclipse. For a solar eclipse. For a lunar eclipse, it's one side of one sheet. It's really not so bad. But imagine doing that for 13,000 eclipses. I'm not sure if that is a triumph of perseverance or if it's just like kind of crazy OCD. But that's what people were able to do then. So let's get back for a moment to this eclipse and talk about how you're able to predict and how eclipses happen. So the same University of Michigan survey that I referenced earlier that told us 88% of the population saw this eclipse asked the survey participants about their scientific literacy. These are questions that this particular author, Professor Miller at the ISR, has been asking Americans for decades, tracking Americans and people in other countries to track their scientific literacy. So 49% of Americans in this pre-eclipse survey could give a scientifically accurate description of an eclipse. The moon gets between the sun and the earth. 62% of Americans in the same survey knew that A, this is actually 2 questions, that the earth orbits the sun, and that the period of that, they're asked, okay, so the earth orbits the sun, does it orbit once a day, once a month, or once a year? If you answered both of those questions correctly, you are in the 62% of Americans. So I've stated this positively rather than saying 51% of Americans could not give a scientifically accurate description of an eclipse. I guess I'm not surprised. And as I'll just say that as they've tracked the scientific literacy of people in different countries around the world, believe it or not, Americans come out actually quite close to the top. It's worse in other places. But let's focus on the science here. So if I can have the lights now, Monica. So of course, the phases of the moon happen because the moon is illuminated by the sun, but as it goes around the Earth, it presents a different aspect to us. And so the face turned to the sun is lit up, and we see different parts of it. And when the moon comes in between the sun and the Earth, we get a new moon and possibly an eclipse. Okay, thank you. So if the moon orbited the Earth in the same plane that the Earth orbits the sun, then we'd get an eclipse once a month. Every time the moon passed between the Earth and the sun, it would cast a shadow on the Earth. But the moon's orbit is tilted with respect to our orbit around the sun by about 5 degrees. And that means that the shadow of the moon may miss the Earth. In fact, it usually misses the Earth. Usually when the moon passes between the Earth and the sun, it's a little above or a little below. And so the shadow of the moon misses us. So it takes a special arrangement for the shadow of the moon to fall on the Earth. It has to happen that the moon passes between the Earth and the sun at the same time that it's passing through the plane of the Earth's orbit. In other words, it passes actually in front of the sun and not above it or below it. So here is a picture of that. These places where the moon crosses the plane of the Earth's orbit, crosses the ecliptic plane, are called nodes. So here we have in the front here a new moon occurring when the moon is crossing the plane of the ecliptic here. It's crossing a node, and so we could get an eclipse there. On the other hand, at these points on the left and the right, where the moon is above or below the nodes, the shadow of the moon misses the Earth. I should say that when the full moon happens while the moon is crossing a node, then the moon can hit the Earth's shadow like it did earlier this week. We didn't have good viewing in Ann Arbor for this. We were not well situated. We were a little too far east, and also it was kind of hazy that morning, but you could have watched this on the web. And here's a picture of the super blood blue moon that we had on Wednesday. So here is a plot showing the phases of the moon and the latitude of the moon, plus or minus above or below the plane of the ecliptic. So it swings between plus and minus 5 degrees during 2017. So I've plotted the phase of the moon as well as its elevation above or below the ecliptic. And I've plotted vertical lines through the places where the moon is new. So you see here in February of 2017, the upper left-hand line, that there was a new moon there. I don't know if that's the end of January or the beginning of February, but the moon was too high, so the shadow missed us. At the end of February, or maybe that's the beginning of March, the new moon happens sort of close, so that yellow band is the width of the sun. So if the new moon happens in there, we have a chance for an eclipse, and I've drawn those favorable eclipse times of year with green vertical lines through the plot. So the new moon happens at a node at least twice a year. There are 2 eclipses somewhere on Earth every year. They don't have to be total. Some are partial. In fact, this one that happened last year early in the year was a partial eclipse that was visible over Antarctica. So you probably missed it. Then there's these other ones, and then here is our August one, where the new moon happens again near a node. So why doesn't this happen more often, or why does it happen at all? Why doesn't it happen on a sort of regular cycle? So that gets to the question of what's the period of the moon? Well, it depends on what you mean. So most of us, when we talk about the period of the moon, might say, well, from new moon to new moon is a lunar month. And so here I've illustrated an example of an interval between new moons in purple there. And that time interval is called a synodic month. There's some nice vocabulary associated with this, old-fashioned astronomy vocabulary. A synodic month that is 29.53 days and change. The reason that these node crossing, that these full moons don't always happen at the same latitude is because there is another period of the moon's orbit that you can talk about, the period from node to node. And that's not the same as the period from new moon to new moon because the moon's orbit is precessing a little bit. And so this period from node to node, you can see here I've highlighted when it crosses on the way up to the next time it crosses on the way up. That's called a draconic month, and that's 27.21. So every time multiples of those line up, the moon is new and in the same position. So we can, but there's one other, let me go back again, but there's one other thing that needs to happen for a total eclipse to happen at that point. Not only does the moon need to be, dead center on the sun at least somewhere, but the moon needs to be big enough to cover the sun. Now I've got a scale model of the Earth-Moon system here, and if you remember that picture I drew before, you might think the moon should belong about here. That's how it's usually drawn in pictures. But the correct scale for our model of the Earth-Moon system has the moon about 30 Earth diameters away, kind of over here. So the moon is more like this ball over here relative to that globe of the Earth. And through a fantastic coincidence, the sun is 400 times further away than the moon, and it is also 400 times bigger than the moon. And so the apparent size of the moon, as seen from the Earth, is the same as the apparent size of the sun. So in the same scale model, the sun would be what, about a 12-yard diameter ball 2.5 miles away, kind of somewhere near the bell tower on North Campus or something like that. Same apparent size as this. But it is so close that the distance, the exact distance from the moon to the Earth really matters as to whether it will cover the sun or not. And the other thing about the moon's orbit, besides the fact that it is not in the same plane as our orbit around the sun, is that the moon's orbit is not circular. And so the apparent size of the moon varies from month to month. You can see here the simulation of the phases of the moon in 2017 as the moon gets further away it is small, so this little slider on the far right is showing its distance in Earth diameters. And then as it comes in closer, you can see its apparent size getting larger. So the supermoon that you've been hearing about very recently happens when the full moon occurs at the moon's point of closest approach to the Earth, so its apparent size is also as large as it ever gets. When the moon is at its furthest point from the Earth, which is called its apogee, it's not big enough to cover the sun. It needs to be in this kind of front half of where it could possibly be. So when we get the longest solar eclipses is when the moon is at its perigee, at its closest approach to the Earth. So that is actually yet a third period, a third lunar period, the period from perigee to perigee, closest approach to the Earth to the next closest approach to the Earth. And that's yet a different, it's not depicted on this plot, so I'll just write it down. That's called the anomalistic month, and it is just a little bit longer, a few hours longer than the draconic month. So in order for the same conditions to recur, we need to find commensurate multiples of all three of these different periods. You can think of these three periods as like gears on a wheel, and have three interlocking gears, paint one tooth on each of them red, and keep turning until all the red ones line up again. It depends on the number of teeth. So this leads to the concept of what's called the Saros cycle. So if we take this synodic month, new moon to new moon, and multiply it by 223, we get 6,585.3 days. If we take the draconic month and multiply it by 242, we get a very, very similar number to within a few minutes. And if we take the anomalistic month, perigee to perigee, and multiply it by 239, we get, again, almost the same number. So that's how many times we need to turn those gears around in order to get the red teeth pointing up again. So if we have a configuration of the Earth and the moon and the sun that results in a solar eclipse, then that same configuration will repeat itself every 6,585.3 days, which is about 18 years, 11 days, and 8 hours. So that is the interval between repeating families of eclipses. And there are many such families, of which our eclipse last summer was one. So here's this illustration of gears, through the three different periods. And when you have even multiples of, least common multiples of all three periods, you get a new eclipse. Okay? Now, the Saros cycle is interesting because it's nearly a whole multiple of a number of years. Right? It's 18 years and change, which means that these related eclipses happen at nearly the same time of year, which means that they will occur at nearly the same latitude. Okay? So, in fact, ancient people knew about this, and there is a mechanism that was recovered from a Greek shipwreck that happened in the 1st century BC. It was believed that this device was built in the century preceding the shipwreck, but it is gears that archaeologists and historians have analyzed and imaged and kind of figured out that this so-called Antikythera mechanism could predict the positions of the sun and the moon and the planets, and it knew about the Saros cycle. Saros is a word; it's not a person's name. It means 3,600 in Babylonian root, apparently. So it's an amazing mechanism. Nothing remotely as complex was built in Europe for another 1,500 years. It's really remarkable. It's not even clear who built it or with what kinds of tools and technology. But this literal clockwork universe was known even to ancients. So they're probably not at the level where they could say, be in Salem, Oregon at this time on this date. So, all right. So if these eclipses come in groups, then why didn't we have an eclipse like this back in 1999? And the answer is we did, but it happened over Europe and Central Asia. Why? Because of that extra 8 hours in the Saros cycle, the Earth has rotated 1/3 of the way around. So instead of happening here, this eclipse happened there. But it's the same trajectory, the same latitude. It's really a copy of ours, just shifted 8 hours to the east. The next eclipse in this cycle will happen in the year 2035, and it will happen over Asia and the Pacific. Our eclipse last summer was probably the most viewed eclipse in history, but I expect that record will be surpassed by this one, which passes directly over Beijing, China, directly over Pyongyang, North Korea, where Kim Jong-un will be sure to take credit for it. It passes just north of Tokyo. So it will be viewed by very large population centers in Asia before it makes its way out over the Pacific. And then this cycle will continue. So the next such eclipse will take, you see they're also migrating slowly to the south. So there's this one in 2053 that will take place over North Africa. So you have to wait 3 Saros for those 8 hours to add back up to about a day and put the eclipse back at the longitude where the earlier ones happened. So the next real copy of our 2017 eclipse will happen in 2071, and it will be over Mexico and the northern part of South America. So stay tuned for that. And then finally, 2089. So this keeps going. This pattern repeats itself every 18 years, 11 days, 8 hours. But it doesn't last forever, because as you can see, these eclipses are gradually migrating north to south. So this particular Saros cycle is labeled Saros 145. It began with partial eclipses near the North Pole in 1639. It will end with a partial eclipse at the South Pole in the year 3009. Altogether, there will be 77 eclipses in this series, of which 34 are partial, 41 are total. One is annular. That means the moon doesn't quite cover the sun, so you see a ring. And there'll be one hybrid eclipse, the rarest kind of eclipse that is a total at some places along the path and annular at other places along the path, depending on exactly your distance on Earth to the moon, because the Earth is round. So those are extremely rare. So here's an animation of this cycle, starting at the North Pole, going from north to south, total eclipses there, and then ending in about the year 3000 with partial eclipses near Antarctica. Okay. So these eclipses go either from north to south or south to north over a period of say, 12 to 1500 years. They tend to produce mostly in the low 70s number of eclipses, but it varies a little bit. So there are many such cycles, of which I think I said on the previous slide, there's 40 of them currently active at the moment. Now, that's not the only kind of a game you can play with these multiples. I think it's interesting to think about other ones. So here's another one. We have these 2 periods again, the synodic and the draconic months, that are, remember, new moon to new moon and node to node. So if we take this synodic month and multiply it by 358, we get this number. We take the draconic month and multiply it by 388.5. That's important. We get almost the same exact number. This is another cycle that has a name called the NX cycle. It's 28 years, just short of 28 years, 29 years minus 20 days. And it is not an anomalistic, it's not a multiple of an anomalistic month. And so these eclipses do not need to be the same type like they are in a Saros cycle. But that extra 1/2 means that they happen at the opposite node. And so they will happen at the opposite latitude as its friend. So the NX friend of our last eclipse, and it's called an NX cycle, by the way, because a new one starts shortly after a Saros cycle ends, and then a new one begins. So as one is incoming, the other one is exiting, and that's the term coined for this cycle in the 1950s. So there is the NX partner of our last eclipse. You again recognize that characteristic kind of S-shaped trajectory, but it is at the opposite latitude here in the South Pacific. And it was an annular eclipse because it was a different time of the anomalistic cycle. The moon was further away. You can label every eclipse by its NX number and its Saros number. They make this lovely mosaic of eclipses. So the Saros indices are going, each vertical cell is separated by one Saros. So you see partial eclipses in red at the top and the bottom, mix of total and hybrid and annulars in the middle, and then the NX number is going down like that. And this is just a little piece of the whole thing. You can extend this to thousands and thousands of eclipses over 25,000 years. This was used to extend predictions into distant antiquity before computers could do it. You're making use of the clockwork-like regularity of these cycles. So it's kind of cool that you can characterize all this stuff for many thousands of years. There are very slow changes to the Earth's and the Moon's orbit that ultimately limit our ability to exactly predict the circumstances of eclipses thousands and thousands of years in advance. But certainly for purposes of most human timescales, this is really pretty good. So let's get back now to 2017. So years went by, decades went by. Even though we were the best of friends in high school, you tend to lose touch. And so it had been years since I'd heard from any of these people. And then about a year and a half before last August, I got an email from Jeff. Turned out he'd grown up and gotten old too. Who knew? He's now a neurologist out in Portland. He said, there's going to be a total eclipse near my house in 2017. Remember that one we said was going to be in the far, far distant future? It's here. Grab your floating car. No, that didn't happen. But he said, let's get the band back together. So, sure enough, we got the band back together. And the best part of it was that he tracked down Mr. Matzik, our 8th grade science teacher, who had retired many years before. He's in his late 70s now, but active and spry and fully engaged in life, and was very excited to see another eclipse and to meet up with us. So he flew out too. So there we are in Scio, Oregon, a little bit south of Portland, where we set up camp at a beautiful site on a ranch. So many things have changed since 1979, not only the appearance of the participants, but modes of transportation. So there we were in Winnipeg, outside the city hydro plant in the dead cold of winter in 1979, and different camper, different setting, but different season. There we are. There is Mr. Matzik on that camper in 1979, and there he is today, looking great. There's Rob and me. I'm trying to be serious, you know, and like, and these people. But at the end of the day, we all made it there. We had, of course, this time it's with families and kids and extended groups of friends. It was just wonderful. And so here was the view from our site in the moments before totality.
20 seconds. 20 seconds.
20 seconds.
Woo!
Nothing you can read and learn in advance about cycles and the moon and the sun and all that can prepare you for the experience of watching the Earth get progressively really dark and then all of a sudden watching the sun go away. It engulfs the world. And if you've seen pictures just of the corona, it is the size of your thumbnail held at a distance. It's a tiny, tiny part of the environment, and it's stunning. It's weird as all get out to see this thing in the sky. But even more remarkable is the complete engulfing of the world by darkness, by silence. Animals react differently. People react in strange ways to eclipses, and it's hard to predict how you will react until you've experienced it. You can completely understand why ancient people or pre-scientific societies who didn't know what was going on with eclipses found them completely terrifying. It is a visceral sense of the world coming to an end. If you know what's happening, it is still a visceral sense of the world coming to an end. And it evokes extremely powerful reactions in people. People laugh, people cry, people, kind of lose control. It's a remarkable thing, the way the world is swallowed like that. Here is another view of the eclipsed sun over our site and the beautiful diamond ring that we saw as totality ended. Here's a view from above our site taken by a drone that we launched. So we parked a drone over our site looking to the west, and I've sped this up by a factor of 5 so that I can finish this talk on time. But there we are down there in that little white tent you can see at the end of the grass strip near the water. And we're looking west, and so we'll see the approach and then the end of totality. The shadow of the moon is moving at 2,300 miles an hour. It's moving about 3 times the speed of sound. So the speed with which it swallows the world is really amazing. So here it's getting dark. So meanwhile, up in the sky, it's getting very dark. It just is night. But you can see in the distance, there's already light. At one point, we tried to point it up to the sun and couldn't. It doesn't point that high. So we put it back. And here comes the shadow. And it's over. 2.5 minutes is all. Now, meanwhile on the ground, that couple at the lower right. As soon as so this is Jeff's son, Dylan, and as soon as the total eclipse ended, he proposed to his girlfriend, who accepted. So the circle of life goes on. I think if you had said to any of us back in 1979 that at that eclipse in the future, one of our kids would get engaged, we wouldn't have quite been able to comprehend that. And meanwhile, my bride was a few yards away under that white tent, and we were over here with this little telescope, which you see right here. So, despite my friend Rob being a pest and in the way, I was trying to do science again, and so here's what we were up to. We were one site of a project called the Citizen Kate experiment. Matt Penn, an old friend of my wife Kate's and mine, is a solar astronomer at the National Solar Observatory. So he's like me, he's an astronomer, but he's one of these people who's smart enough to work days. So his idea was this. This eclipse is going to cut a wide swath across the United States. You notice all these eclipses, a lot of them are over ocean. There's a lot of water on this planet. But this eclipse cut a 2,000 some mile wide path. It took the shadow of the moon 90 minutes to cross the US. And so his idea was, let's put the same set of equipment at sites all along this path with the same camera, the same software protocols, et cetera, train all the observers along this path to take the same kinds of data for this experiment and piece it all together into a 90-minute movie of the inner corona and do some science that it's not possible to do any other way. Understand the evolution of the inner corona over time. It's hard to even do this from space. So this got a groundswell of support. It got also funding support from NASA and the National Science Foundation and some private money. And so at the end of the day, 66 sites were set up from coast to coast. Here we were out in Oregon, Kate 002b. And so we practiced a lot over the summer and the weeks preceding the eclipse to get everything exactly right, because you can't consult the manual during the eclipse. For one thing, you can't read the manual, but for the other thing, you have to be prepared for the fact that the eclipse is going to take your breath away, and you want to have it as automated and as routine as possible. One of the things you must remember to do when totality starts is take the solar filter off. You don't need it anymore. So what this telescope then did during totality was, under the control of a little device called an Arduino that was talking to the camera, it was snapping 8 exposure sequences that were then stacked into a single HDR image over and over and over again as long as totality lasted. So here is the shortest exposure. You can hardly even see it, maybe, except for a few prominences there near the solar limb. This is a 0.4 millisecond exposure, and then 1.3 milliseconds, 4 milliseconds, 13 milliseconds, 40 milliseconds, 130 milliseconds, 400 milliseconds, 1300 milliseconds. So this whole sequence took a couple of seconds to take, and then they get stacked using the best parts of each image into a single image that, like the one you see here. So these beautiful images. You can further then start image processing these things. You can run this through something called the Sobel filter that is a edge detection and edge enhancing algorithm to get details of the fine structure of the coronal filaments like this. And then you can start to put it together. So this is an extremely preliminary look at using just a small fraction of the total data from Kate of this eclipse. There's lots and lots of work to do to align the images properly and so on. But this is looping. But you might be able to glimpse, particularly in the maybe around 4 or 5 o'clock, some hints of evolution in some of those filaments, maybe also up near the top at around 1 o'clock. Here's a close-up of this one prominence on the limb. And you might imagine you see some evolution going on in that structure there. You can also see different pieces of the lunar limb coming and going as the eclipse progresses, features along the limb of the moon. So this is very preliminary, and I am not myself involved in the analysis of this data. This will be done by proper solar astronomers. I'm busy looking in the opposite direction. But we're looking forward to, having contributed to this, and we're glad to have contributed to it, and we are looking forward to some of the first results from this coming out, we hope, later this year, that will have many citizen scientists as authors. Many of these teams along the route, these Kate teams, were high school students, like I was 38 years ago, and I hope that they will be inspired as a result of this to pursue careers in science. So suppose that you missed this eclipse. You were one of those people who stayed home, or you were lost in the ocean somewhere. Or suppose you saw this eclipse and you thought it was great and you want to see another one. What should you do? Fortunately, you don't have to wait another 38 years to have an opportunity relatively close at home to see another eclipse. On April 8, 2024, the next great American and Mexican eclipse will happen, and it will follow this route, coming this time from southwest to northeast. And as you can see, it comes rather close to home. Let's look and see what it's doing in the Michigan area. There it is. There's the path of totality. It will pass through my hometown of Hudson over here, so some of those people won't have to travel at all. But it just misses us. In Ann Arbor, it will be a 98.3% partial eclipse. It's going to be very dark. It should look about like that. Now, if you've seen a total eclipse, you will know what the essayist Annie Dillard is talking about when she says, seeing a partial eclipse bears the same relation to seeing a total eclipse as kissing a man does to marrying him. So my advice to you in April of 2024 is don't kiss the man in Ann Arbor when you can marry him in Cleveland. Or something like that. I think I need a more inspiring slogan for that eclipse, but I'm working on it. Okay? So, you don't have to drive much more than, 60 or 80 miles. Toledo will work, but the eclipse duration in Toledo will be short. You want to be as close to the center line as possible, so that puts you near, Lima or Findlay or someplace like that, or Cleveland if you want to go east. However, we all know what the weather's like in Michigan and Ohio in early April. We might not see the sun all month anyway. We might not even know. It's just kind of dark today. So here is a map of the historical cloud cover data for April. And it will come as no surprise to anyone who's lived here that the odds of it being cloudy in April at this, in this location are kind of 50, 60%. The smart money for this eclipse is on the sites in Mexico, which is also where the duration is the longest. So I'll have to choose between going to my hometown, where I would sort of like to see it, and going to some place where I'm pretty sure I really will. But those are your options, putting that out there now. Okay. Now suppose that you really still don't want to leave Ann Arbor. You're just going to stay put and let the eclipse come to you. What do you need to do? Well, you'll have to wait a while. But on September 14, 2099, you will get your chance. Some of the youngest members of our audience might make it till then. The rest of us can be unfrozen. But you know, if you look at this, it's still cutting it kind of close, isn't it? So can you really see this as a total eclipse in Ann Arbor or not? Depends on where you are. You would like to be on the correct side of the Huron River to see this eclipse. You do not want to be on North Campus. You do not want to be in Northwood housing. But here on Central Campus, we'll get our chance. I'm glad to see that Pinball Pete's is still there in 2099. Everything's still a quarter. But let's zoom in now on right here to see what things will be like where we're currently sitting. I've traveled to the future, and I've come back with a map of our campus from 2099. There have been a few changes. Chemistry was renamed back in the mid-2050s. The physics department is now the Institute for Predictive String Theory. I'm glad to see string theory is finally amounting to something that... The parking structure across the way is a place now where you can leave your hovercrafts. They got rid of the library some time ago. That's now the Zero Gravity Indoor Sports Center. And here at the Saturday Morning Physics Megaplex and Luxury Suites in 2029, we will experience totality for 1 minute and 3.8 seconds. Now, that day is a Monday, but the Saturday morning physics talk, the following Saturday, the 18th, should have a ready-made audience with interesting stories and interesting experiences to share, and perhaps one of the youngest members of our audience will be an old man or woman and can even give that talk. I hope to be unfrozen and come and attend it. Okay, so in fact, the only person I'm really betting on being there is Mr. Matzik, because as far as I can tell, he is timeless. So, so thank you all very much.